there's definitely a desire to be able to have compute operations control graphics operations. And in order for that to happen, you need to be able to let compute specify state. And there's a lot more to that that I don't know that I can say very much more. But it's definitely on everybody's radar. Anything else? Yeah.
There's a lot of research going on for these heterogeneous architectures where you don't have 512 of these little cores. Maybe you have 256 of those little cores and then one or two big cores.
Yeah.
So basically you have, this is really good at parallel, use it for parallel, this is really good at serial, use it for serial. Are you guys looking into that kind of thing at all?
Now, are you thinking on all on chip?
Yeah.
Yeah. If we're looking into it, I'm not one of those people they tell about. And if I were, I probably couldn't say. That having been said, I know we look into pretty much everything.
Okay.
If there's a point at which it makes sense, I suspect we will. However, that having been said, you would spend at least as much time designing those larger cores, if not, well, if you were to start from scratch, you would spend as much time designing the large cores as the small cores, but you would get far fewer of them. That being said, we spent so much time designing the small cores that we would essentially be starting from scratch designing the small cores, and it would be a very hard game indeed to catch up with Intel on that. If at some point it makes sense to do, like it looks like we can, I know we will look at that. One thing I think I can say is that even some fairly radical things our hardware teams look at. So I know yesterday internally we had a presentation from some guys in Portland research lab. I want to say Portland State, but I can't remember which university it was. And they were presenting clockless circuitry. And I don't know if you guys are familiar with this or not, but basically the clock in a chip is a really cheap and easy way, or traditionally was a cheap and easy way to design circuits because you know that your very slowest component can always finish its computation between each clock cycle. And so you just tie the whole system together with the clock and you're done. The problem is, as we get faster and faster and smaller, the clock takes up more and more circuitry in the chip and it takes up more and more power. To the point where you're looking at chips that spend 80% of their power or more on the clock, and a huge amount of the chip space on the clock. And when chip space is so valuable, that starts becoming really expensive, and so you have to start looking at different ways to do things. And asynchronous circuitry is a way of essentially ditching the clock and letting each component tell the next component, hey, everything's done, and you can take my data and start your processing with it, and just cascading things through that way. It's pretty crazy. Everybody has been talking about it for a long time, saying eventually we'll need to do it. Eventually clocks are going to run out, we're going to have to do that. The problem is there haven't been good tools. The verification and debugging tools weren't very good, and that's what these guys from Oregon are working on is verification, debugging, finding a way that companies like NVIDIA, companies like Sun, big hardware companies can adopt this and actually verify it before we actually tape out and burn the hardware. NVIDIA's bread and butter is emulation, verifying everything before we ever produce a bit of silicon. And if we can't verify something in emulation, it's a non-starter. We'll never do it. And so now there's a hint that maybe this stuff might start being usable, and so the researchers are starting to say, hey, you guys interested? So I mean, that's one of those way out there sorts of things. I can't even predict if we'll use it or when we'll use it, or even if we're doing anything more than just being kind to these researchers and letting them tell somebody about their stuff. But hopefully that sort of answers your question.
Yeah. I guess I had another one too.
Yeah.
The memory unit, with the virtual memory, do you guys allow virtual shared memory? So if you have two processes that are both have this page in memory that is X page or whatever, do you allow it to say, oh, this page is the same between these two, let's just use it for both?
We certainly could. I don't know that we do it between processes, but you can have different shares within a same process, and you can share that data between shares. And that's actually, OpenCL and OpenGL communicate that way. They use the same virtual addressing space. And it's not at all uncommon to do that within a process. If it becomes important for people to do it cross-process, I expect we'll find a way to expose that, but I'm not aware of it being exposed right now.
Does CUDA communicate with OpenGL using a similar mechanism, or is that just not possible?
Yes, it does. CUDA and GL interoperability is a big thing. It, as far as I'm aware, well, I think I would know, does not exist on the Mac. And it is unlikely to exist in the near future on the Mac because the Apple driver model is so dramatically different from any other driver model. And CUDA, although CUDA works on the Mac, they work in a different way than the OpenGL driver and the OpenCL driver. So I won't say it's never going to happen, but it's not going to be this month. But on every other platform, it does interoperate, at least for us. Yeah.
So early on, when Fermi was announced, there was a lot of talk about how NVIDIA was basically giving up on the gaming market and giving everything to ATI. And I assume that there are a lot of good reasons why a lot of more energy is directed toward just general purpose computing. But I just want to know what your answer to that.
Yeah, so I'm not sure who was saying we're giving up on gaming. I can tell you absolutely for certain, with Fermi, with the next generation beyond Fermi, for the foreseeable future, we are not giving up on gaming. We spend a tremendous amount of time making sure that games run right. And the desktop market is actually a very lucrative and important market for us. So gaming, even if we didn't make the majority of our money from gaming, and I can't say whether we do or we don't, it would be important if for no other reason than what gamers do, people tend to follow. You know, if you've got some enthusiast, we might not make the bulk of our money off the enthusiast, but then they go tell their family, oh yeah, you're getting that system from Dell? You know, NVIDIA's got the best graphics part, so you might as well just opt to get that. That's actually, it sounds silly, but that's important. So for that reason alone, we couldn't give up on the gaming market. But also a lot of the innovation for what's coming next in hardware has traditionally come from there. I think what people are a little surprised at, I guess, if anything, is how big the general purpose computing market has become. And so our focus on general purpose computing can make it look like we're leaving gaming behind, kind of because it's the next big thing. I think ultimately it will probably be a much more lucrative market long term than gaming, but I don't think gaming will ever go away because it will always be a lucrative market.
Last question, Bob.
Yeah. Isn't it also possible, along the same lines of that question, is that as the game developers become more comfortable with the parallelization that is offered from the GPU stuff, that gaming almost kind of moves in a different direction to jump on that bandwagon, like you were mentioning with the real-time ray tracing and stuff like that?
Absolutely.
In which case you're in a good position both.
Yeah, and I think we will, at least for any future I can see, always keep certain fixed function units on the graphics card. So you know, we talk about how fixed function is going away. Well, that's only kind of true. There will always be certain fixed function. Clipping, I have trouble seeing that go to general purpose. Rasterization, we can do rasterization so much faster than any sort of general purpose thing can do with the fixed unit. That'll stay there. And rasterization is going to continue to be important no matter what for ray tracing and for any sort of graphics load. So yeah, I mean, they will definitely spread out into general purpose, without any doubt. And ray tracing is one of the big reasons. But yeah, I think it's just a general purpose thing. Gaming is parallelizable, so they will use us as a parallel architecture.
All right, let's go ahead and thank the speaker. And then a brief announcement for those of you that are